Okay, so my name, as has just been said, is Professor Nick Harris, and I'm a professor in the SEMS group at Southampton, which is Sensors and Electronic Materials. The talk today is going to be on intelligent sensing technologies, examples of sensors and the IoT for the environment. And I'm going to talk a little bit about what I mean by environment and also what I mean by some of these sensors as well. So it was interesting to hear the previous talk because obviously the security is quite important. We've done some work on security, but I'm not going to talk about that today. We're going to talk more about some key applications. So a little bit about my background. I've been working in sensors and sensor systems for a very long time on various projects, and here's some names of some of the projects that that I have worked on, and you can see they all to do with sort of sensors in fairly sort of difficult environments really, and the one we're working on at the moment is sensors for embedding in bearings for condition monitoring, and that's obviously a very difficult environment to try and measure in. But my work in sensors has led me to wireless sensor networks and also sort of energy harvesting as well to power these things, which I'll be talking about in a couple of minutes at a time. But we also need to put some definitions in really on what we mean by the Internet of Things or the IoT. And my view is it's just devices connected to the internet, but it is developing into a form of distributed system, and we've heard about that in the previous speaker as well. And it's starting to be known as Industry 4.0. Now, Industry 4.0 isn't really defined anywhere, so it was interesting to hear that there are lots of standards and things being put forward for it now. It was really some marketing words just to get some interest in this kind of area, but the sort of definitions you can see is going from the first industrial revolution of water power and steam power through sort of development of electricity and assembly lines, a bit more computer and automation, and finally into cyber physical systems, which is sort of where we are now. But environment's something that is difficult to define as well. The environment can be many things. It can be outside in fields, and I'll be talking a little bit about environmental monitoring in that respect as well. It can be inside factories, which is typically where Internet 4 might be. Possibly inside the human body, space, and even embedded in structures, which is starting to be referred to as structronics these days. So the environment can cover many fields. So we'll look at some of those with some examples going forward. But what's common about this, in all these environments, we've got things that are common to it. We want to sense something usually, and that's fine. But how long do we want to sense it for? So if it's an agricultural sensor, you might want to sense for at least a growing season, for example. Ideally, you want to sense for a lot longer. But that introduces all kinds of problems about drift in the sensors, battery lifetime, and you don't really want to be introducing batteries into the environment if you can avoid it. How do we want to do it? Do we do a single point measurement, or do we do a multiple point measurement? There's advantages and disadvantages to both, and maybe some of those will become a bit clearer as we go forward in this. And do we process the information or the data on the sensing point or the node, or do we relay it to a central point and process it centrally? Again, there are pluses and minuses, and some of you may recognize processing on node as being a sort of an evolution of edge computing, which is currently very trendy at the moment. But whatever, it implies a systems approach. The embedded sensor is no good on its own. There's got to be a whole system around it. And I say, think about the sound of one hand clapping, and you get the idea of the usefulness of the sensor on its own with no communication and no power. So this leads us into this sort of definition of a sort of a sensing node, if you like. And I termed it the sensor nexus, where the nexus being a sort of a meeting point of several different requirements. And so we've got the sensor itself, which is fundamental to what we want. This is why we're developing this whole system, because we want to measure something. We need to power it, and that in itself can be a problem depending on the environment you find yourself in. And there are all kinds of questions there you might want to ask yourself. How long does it need to last, this power supply? Should it be rechargeable? Can it be wired? Makes life much easier if it can be. Do we have to harvest or scavenging energy? And if we do go down that route, we need to consider the environment that we find ourselves operating in. The sensor itself has its own requirements. Does it sense what we want? I mean, it sounds like a silly question, but you'll find in a lot of papers, particularly on wireless sensor networks, that people are sensing things because they can and not because they want to. The sensors that there's a lot of these sensors exist, but there are quite a few requirements for sensors that don't exist yet. And so people tend to be using proxy sensors or inferring information from the sensors that do exist. And sensor development, as I'll hopefully show in a minute, is actually a tricky thing to do to get right. So we've got a lifetime issue with the sensors. How long do they last? How often wear out? Their accuracy, how accurate do they need to be? It's not going to be a laboratory grade sensor, but it needs to give you enough information to make the whole thing worthwhile. And then we've got a sort of a control point on here where we're going to look at how do we deal with this information. We've then got communication issues as well. Range, what's the range of this system? What's the reliability of the communication system? Does it depend on atmospherics, for example? Security, jamming, does it have to be real time? Is it going to be wired or is it going to be wireless? But either way, we've got to get information out of this sensor to the point where whoever's asked for this system can actually make use of that. And then there are all kinds of other factors as well. Cost is very important, because if you're going to have a distributed sensor network, there are going to be lots of sensors, and they're going to be, the cost per sensor becomes important then. Are they going to be disposable? Are they in fact going to contribute to pollution in the environment if we don't get them back? Deployment, how do we put them where they are needed? And that's quite an important problem as well. So there's a lot of issues that have to come together to make a sensor in the environment work properly and give you the information that you want. But I like to approach this from the point of view of an application rather than having technology driven, because fundamentally we're looking to solve a problem. And when you look at this, this usually comes to a value of information issue. Whoever's wanting this system wants their questions answered, but they don't really care about the nature of the solution. And there's an example here. I'm saying that if I'm tracking a target, for example, as a user, I don't care about how it's tracking the person. I just want to know where the target is. So from a user's viewpoint, it's important to define the problem at the front end, and then look for the technology that can solve your solution. Don't go the other way. Don't start with the technology and then look to solve a problem with it, because that's a compromise, and compromises don't work very well in these situations. So there are lots of problems that you can look at. Fixed area sensing is one, long-term monitoring in a fixed area as well, so fields and things like that. Monitoring a farm, as I said, perimeter of a building or inside buildings, quality of air, very, very important these days, air quality monitoring. Difficult environment sensoring, inside equipment, infrastructure, bearings, bridges, inside jet engines, very important to monitor what's going on in the jet engine and at least try and predict if it's going to fail or when. Inside the human body, instrumented hips, for example. Or perhaps you just want to deploy a network really quickly to help in emergencies, such as firefighters going into buildings wanting to know what's going on in there and where everyone is. And there's a big area emerging now of autonomous mobile networks, sometimes called manets, so swarms and things like that. But there's different approaches for all kinds of different problems going forward. So I'm going to go through 3 examples, and hopefully this will inspire some ideas and give you some idea of how we're thinking, at least. So I'm going to talk about a sensor system in industrial environments, which is going to be for monitoring a rail bearing and track condition. I'm one of the founders of a company called Perpetuum, which exploited and developed technology of doing just this. And I think it's actually installed in some trains in Pakistan now as well. But that's a worldwide reaching company now. I'll talk about that and their technology going forward. And I'll also talk about a sensor for environmental monitoring, which is actually a chloride sensor, which is measures chloride transport measurements in soil, and I'll explain why that's important as well. And then briefly I'll talk about some work that we've just published where a sensor system was installed in some lemon farms in Pakistan, and the yield of the lemon farming has been improved as a result of this. So that's quite a important and interesting result that we get from a relatively simple system. So going back to the industrial application of trains, what's our motivation? So what happens when a bearing fails on a train? So here's a train. It's stopped on a bridge. It didn't have a choice. Its bearing seized, and it happened to not be able to go any further while it was on this bridge. The bridge happened to be made out of wood. The bearing, because it had seized, had overheated, got hot, and stepped far to the bridge, and that resulted in, first of all, the bridge being destroyed, the train having issues, delays to all kinds of things, and $2 million worth of damage. And there's a link there if you want to go and read about the bad day that people had there. But in general, if you have problems on trains, usually a bearing failure on a train, it leads to late trains. It's not like you can overtake a broken down train. The loss of the assets. In certain countries, it leads to fines because you haven't delivered on your contracts. Certainly leads to unhappy customers. Can lead to potential deaths and lawsuits. So all these things are things that we'd like to avoid if possible. So a sensor to measure bearing health seems like a good idea. And how do we detect bearing health? We have to look into that, but basically we'll look for the vibration of a bearing that's starting to fail. And we can do that with an accelerometer. We need to power the system though. So going back to our Nexus, we have to think about that. And the interesting thing is on goods wagons, there is no power on trains. Trains have no power, only in passenger carriages. So you can't guarantee that there's power there. And even if there is power, it's very difficult to tap into it because it's a safety related issue. So we thought we could power it from vibration. So this is our sensor Nexus again. So we've got a sensor, which is an accelerometer. And we can measure and process acceleration to understand what's going on in our bearing. We can power the bearing or the system from vibration because trains are not the smoothest things in the world. And then we will relay the information through some communication system and capture that and process it. And this is what we did. We developed a sensor system enabled by energy harvesting to allow us to predict the failure of bearings. And here you can see it fitted to a train. It's very easy to fit to the train. You just drill a hole and bolt it on, and that's it. So retrofitting this and installing it becomes relatively straightforward. It leads to reduced operational maintenance costs and improved asset utilization. Operates over a wide temperature range, and turns out that the vibration in trains is much, much higher than anyone ever thought. So there had to be quite a lot of engineering going into this to make it actually survive some of this, let alone power itself from some of these environments that it finds itself in. And lasts for over 5 years. Well, they've been going for much over 5 years now without any problem. And no train fitted with a perpetuum system has ever had a bearing failure that wasn't identified much in advance and was allowed to be swapped out. And so the sort of thing you get from this is something called a bearing health indicator. So this is an algorithm that works out when there's likely to be a bearing failure. And you can see over a period of time, so we're talking a period of months here at the bottom scale, the bearing health index is starting to rise, which implies that the bearing is not doing too well. And then at some point, go back, sorry, we end up changing the bearing before it's failed. And then you can see that the new bearing is nice and smooth, and here's the damage that we can find in the bearing. So this allows us to program maintenance, and it avoids the issues of trains breaking down in the middle of the track and all the other issues that are associated with that. So you can plan your maintenance because you've got several months to plan this maintenance, having seen this index starting to rise. We also discovered that not only can we monitor the bearings, but we can also monitor the track with the same sensors. And certainly in the UK and probably many other countries as well, we've got this strange system whereby the track is owned by separate company to the train operating companies, and the trains are owned by the train operating company, and they effectively lease access to the track. But these trains traveling over the rail can actually monitor the track as well, because you've got a whole load of distributed sensors going over your rail network every day. And for example, if you get a spike on your accelerometer at a fixed point geographically, then that's likely to be systematic of the track rather than the train going over it. So you can actually create a map of where there might be train issues. Now, certainly in the UK, this introduced some issues with responsibility, because people don't like spending money on the maintenance of tracks because it costs money, and no one want to be responsible for the damage. Now, the main cause of damage on tracks is out of round wheels, so wheels that are slightly out of not round anymore. As they go around, they sort of act as a hammer, and they hammer the track, and eventually that leads to fatigue and track failure. And the question is, who's responsible? The track company or the train operator for this fault? Now, obviously, the track company is responsible for repairing the fault, but should they be responsible for paying for it if it's the train operator whose lack of maintenance on his wheels has caused the problem in the first place? So this led to a lot of issues with actually installing these systems, and political issues, I suppose you could call it. But now it's actually worked out to be very successful for all involved. Everyone gets to save money on it. And the same idea is now being used for other transport modalities. For example, sort of potholes in roads can be detected by, for example, buses fitted with accelerometers and GPS. So again, when they hit a bump, they can relay that position, and you can get early warning or earlier warning of where your holes in your roads might be. So that's quite a useful thing. So here's the sort of information that comes back. This is a map of part of the UK, and this is a section of railway line which the trains that have sensors on are running up and down all day, every day. And there are 4 tracks in this particular piece of railway, and they're shown here as track 1, track 2, track 3, and track 4. And you can see the quality of the track in terms of the acceleration data that comes from the trains going over here. This one's perfectly fine. This one's perfectly fine, and this one is starting to have an issue because we've got a big red area here. So there's likely to be either a crack in that rail or a bit of subsidence or something going on. But at least we can see that early, and then again plan the maintenance with the minimum disruption. So that's a very useful indication of a successful system. So my second example, which will look at environmental monitoring in terms of agriculture. I'll just set the scene for that because key facts are quite interesting. I like to have the context and look at the application. So on a global scale, the population will grow to 9.6 billion by 2050. And here's a graph showing the sort of average prediction of population growth. New estimates indicate that we may be on the sort of lower track, but even so, it's still going to grow significantly in the next few years. And therefore, food production, and not including food used to create biofuels, so corn for ethanol. So food production must increase by 70% by 2050 to allow this to happen. This is a big number. There's a lot of people interested in this. But we've also got this other perfect storm, that the land available for agriculture is reducing. We have more urbanization, but we have other issues as well. For example, pollution of land. So 20% of the world's irrigated land is actually degraded by salt. And salt is not good because salt doesn't allow crops to actually grow. And this is an area the size of France, which is pretty big by anyone's standards, really. And it's increasing every year. And the numbers drive politicians, $27 billion a year in lost crops per year. Now, we don't want to be losing this when we need to be increasing it. And particularly in Australia and places like that, it's called the White Death. And this is salt encrusting on the surface. And obviously nothing is going to grow here for a long time. So the main reason for this is believed to be due to overuse of water and unsympathetic farming practices. And where does this water get used? Well, it's used in irrigation. And there's some quite frightening facts here as well. 70% of all the global freshwater withdrawals are used for agriculture. Irrigated agriculture produces 40% of the world's food from only 20% of the agricultural land. So this is good. You know, we're getting, this is a really good thing. So irrigation produces good results, extra yield and everything, but we're using too much of the water. Just having a look. Oh, okay, fine. In case it all gone horribly wrong, but we seem to be good. And I've done a lot of work in Australia, and irrigation uses 80% of Australia's water resources. 80% of Australia's water is used in irrigation, and produces 30% of the nation's agricultural production from only 0.5% of the nation's agricultural land. So there's a lot of scope for increasing in Australia, certainly, the amount of irrigation that happens. But Australia has this problem with salt issues. And then there are other things which strike me as being a bit mad, really. 80% of California's water is used for irrigation and accounts for only 2% of California's GDP. And a lot of this is because it's a desert and they're growing crops that need a lot of water, such as oranges, which is okay if there's plenty of water. But I think, as we all are starting to hear now, California has a lot of problems, and they really should be doing something about it and not using more water. But anyway, that's what we got. Bottom line is, if we are going to increase food production to 70% or more, we are going to exceed our current water supply. We haven't got enough water to do it if we carry on the way we are. And another example, in China, small rice farms are moving from 3 crops per year to 2 crops per year as employment moves to cities. China is an interesting case. They're moving people into cities from urban areas, and a lot of it is sustenance farming that was done there. And so we're instantly losing a significant amount of crop production in China because of this increasing urbanization, not necessarily because we've lost the land, but because the labor that grow the crops is actually working in the cities now. So therefore, something like sensors and the IoT and in the field of precision agriculture will be a vital system going forward. So this can really, really help the world's problems going forward. So the future may well turn out to be something like this, with vertical farming, using the tops of buildings. Certainly in the UK, someone calculated if we used the tops of all our supermarkets and warehouses to grow non-arable crops, we would double the amount of land available for crop growth, and would also shorten the supply chain remarkably, since it's been growing on top of the shop. So there's all kinds of novel and interesting ideas, and all these, obviously, because they're a bit unnatural, require some technology to keep them viable. But in the environment in general, there are many things that could be monitored at different stakeholders and at different scales. So here's sort of a picture of the environment, and you can see all kinds of things that will lead to pollution and issues and stuff. Fertilizer, which is a good thing in fields, is a bad thing when it ends up in rivers because it leads to algae blooms and dead fish. So we have to be aware of the scale of our issues. Fertilizing at one point is a good thing, leads to pollution in other areas if everyone's doing it out of control. So we developed a chloride sensor to monitor the movement of water through the environment, because we could inject some chloride and track it. And so the sensor development from this, I won't go into too much detail on it, but just to show you that sensor development is actually quite a hard thing to do. So we wanted a low-cost chloride sensor for salt measurement, so we could distribute it across land and work out what's going on, so we could inform land use change for politicians. So the sensor needs to be long life, last at least a growing season, ideally more. Needs to be low cost because there's going to be lots of them distributed around. It needs to be accurate enough, and it needs to be low power. So they're the main requirements for it. We chose to use an electrochemical reaction, and I won't go into the chemistry of this too much, but suffice to say that a voltage is generated by a surface with that's been coated with silver chloride, which changes by 59 millivolts per decade change in the chloride concentration. So every time the chloride changes, we get a voltage out that changes. But we have to measure that against something because it's just a potential, and we have to have a reference electrode, and this is where the real problems lie. And I'll talk about the reference electrode in a minute as well. So we used a thick film process. This is a printing process, the same technique that's used to make t-shirts. Multiple layers are built up to create a structure, and the process consists of printing, drying, and firing. So we have a ceramic, or some cases a metal, but this is a ceramic substrate, and then we can print our layers on top of it. So we printed a silver conductor to allow us to connect to the sensor. We print down an isolating layer, and this circle here is where our sensor is going to be, and then we add our silver chloride layer on top of that, which is going to be generating our potential. So you can see that we end up with a little sensing area on our sensor, and we can solder to this point here, and here's a sort of a picture of one. Size of this, we're talking probably about 30 millimeters, 3 centimeters long, 5 millimeters wide. So it's a small thing, and they're dead easy to make, and we can print loads of them. It's low cost, robust, and it's self-generating because it's generating its own potential from the pollution that it's trying to measure, which in itself raises some interesting questions. And we may compare this against a reference electrode, and this gives us a fixed potential relative to a known concentration. So we basically have to have our electrode surrounded by a known concentration of salt, and that gives us a fixed reference. And then we can compare the salt content of the soil with the known potential of the known concentration of salt here. And again, we've managed that with the thick film as well, and we've printed some extra layers. We put a porous glass layer down, which we developed, filled that with potassium chloride solution, or silver chloride solution in this case, copped it off with some conducting polymer to keep it in, and that made us a nice reference electrode. Now, did it work? So, yep, here we are. We've got 7 sensors being measured against changing chloride concentration, and you can see we've got this wonderful straight line, and they're all matched to each other. So this is great. Straight out of the packet, these things work really nicely. And this is the potential they generate, which is a nice number. We're talking millivolts here, so a couple of 100 millivolts or so. And then if you match that against the chloride concentration in the environment that we're interested in, this is 10 milligrams is about where drinking water would be. And this is what chloride sensitive plants can deal with, and this is what tolerant plants can deal with. So we're operating this range. So the sensor's operating in a really good range for agriculture. So we've made a sensor that works really well. It's robust, it's low power, self-generating, and is reasonably accurate. But it took a long time to get there. Can it provide useful data? So we designed a sort of a logging system based on a system from Libellium. It's a bit like Arduino, I suppose, but a little bit more advanced, called a WASP mode. And we added in a power supply. In this case, we just ran it off a battery because we can get these sensors back. And then we really relayed information through an 802.15.4 shortwave radio system to a receiver on the laptop nearby in this case. But we had multiple sensors connected into this one node here through a multiplexer and amplifier. Bit of self-test because we need to be sure that some of these things are working. And then we could log to an SD card and we can stream by radio as well. So we tried that out in a experiment in a greenhouse in Australia. So this is at University of Western Australia. They have some big greenhouses, and we put our sensors into a known environment, in this case a sandy soil, and put them at different depths. Put some salty solution in here and then let it dry out over a period of time just to show what was going on. And this is the last few days of our 2-week experiment. And you can see a diurnal variation straight away in terms of the concentration of salt in the moisture that we're measuring against time. So you can see the 24-hour period, which in itself is interesting because no one had seen this before. And you can see that the sensors that were buried at about 1 centimeter or 2 centimeter depth from the surface were showing this variation. The sensor buried at 20 centimeters was showing very little variation across the 2 weeks. And at this point here, when we're starting to get high concentrations of salt, we were starting to see salt encrusting on the surface as well. But what's important about this is that it's important what time of day you make a measurement, and it's important at where you make the measurement, because a distance of 20 centimeters means that you could measure this and say there's no problem, whereas near the surface you're seeing big problems. What you're really interested in is what is the salt concentration that the roots of the plants are seeing, and agricultural plants like corn and things actually have very shallow roots, so are likely to be seeing this kind of environment rather than this, hence the problem. So it tells us it takes a lot of effort to develop a usable sensor. Distributed sensors can allow much finer temporal and spatial results because you've got more of them. Normally, to find out the salt in your soil, you can actually take a sample and dissolve it and put it into a measuring system, and that wouldn't tell you anything about the distribution of the salt within that soil, just the overall concentration. And you can only take one measurement because you've dug that point up at that point. You can't go back and measure it again. So now, for the first time, we can see that the salt concentrations vary by an order of magnitude, at least in 24-hour period. So this is telling you that the position of your sensor is vital and that the time of the measurement is vital. And this is telling us a lot more about the environment we didn't know before. And what it's sort of telling you is that sometimes it might be better off having no data rather than measuring stuff and assuming that that is representative of the real environment you're in. So I found that quite interesting, really. So in this case, traditional grab sampling, where you take a sample and take it back to the laboratory at a single point every 3 months, will give you a completely different, in this case, wrong answer to a distributed sensor network with a real-time IoT link. So again, it's important to get the right answer by asking the right questions. Data is as only good as as your interpretation of it and understanding what it really means. So there's a picture of a typical environment showing salt crystallization in Western Australia. So this is the salt. This is a freshwater river, believe it or not. But this is salt that's coming through from underground, being driven by rising water tables because people are digging out indigenous trees which have long, deep roots. So these would, the long, deep roots, tap roots, would actually take out a lot of water from the environment and transpire it into the atmosphere and keep the water table down. When you take those away, the water table is allowed to rise, and that brings salt with it. And that's one of the driving factors in this case. So it's maybe counterintuitive if you think about it, but that's what happens. So just to finish off then, I just want to talk about some of the latest results we recently published. So we did an experiment, or a colleague of mine did an experiment on a lemon farm in Pakistan in Gadap, if you're familiar with the area. I've never been there, so I don't know what it's like really. And they developed an internet-connected decision support system. So we were measuring real-time soil moisture data from a local node, so a sensor that was put into the field effectively, looks like this. And that would measure the soil moisture content and relay that back to a central system, which would then send that information to an app to help the farmer decide whether or not he should irrigate or not. And the irrigation process was slightly complicated here because farmers only had access to water at certain predetermined times within a 2-week period. So most people would then say, well, actually, if I've only got water for 1 hour in a 2-week period, I will water for an hour in that 2-week period just to be safe. But it turns out that you don't need to do that. And even taking that into account, this system allowed 35% more lemons per tree from actually 50% less water. If we get 50% less water in irrigation systems, then that means we can double the amount of land under irrigation and not use any more water. And that gets us closer to this issue of getting 70% more food for the same amount of water supply that we need in the next 50 years or so. So this is an early indication that technology can help us to do this. So there's some numbers here in perspective. If you scaled this up across Pakistan's lemon production, you would save 646 megaliters of water, which is a lot. And not only that, you would generate an extra $14 million of revenue for that crop. So it's a win-win situation. And the only issue is how expensive is it to actually install this system? And it turns out to be not very expensive at all. And the system is available for purchase. If any of you have any lemon farms that you want to instrument from a local company to you. And there's the webpage if you want to go and check that out. Or you can look the paper up and get some more detail from that. So in conclusion then, embedded IoT sensors of any description should not just be considered as sensors, but as holistic information gathering systems. I've talked about some of the issues, and the previous speaker that I heard also talked about a very important issue in terms of security for these systems as well. So it's not a simple way of doing things. The application defines the approach, in my view. You need to define your problem and then define your system. And that will give you all kinds of links onto other aspects, such as the lifetime, the cost, the robustness, and what communication system that you may need to use. But the sensor is the vital part of this. The rest of the system supports the sensor in achieving the mission, but the mission needs to be well defined. And that will bring me to the end of my presentation, and I hope you found that interesting. And maybe we can take questions. I'm not sure how the system works, but that's me done.